Hello, everyone. My name is Ji Yong. I'm from University of Illinois at Urbana-Champaign. Today, I'm presenting data obliviously extensions for side-channel resistant and high-performance computing. This work is done with my colleagues Lucas Xiong, Mohammed El-Haj, and my advisor, Professor Christopher Fletcher at UIUC. Okay, here's the outline of my talk. So during this talk, I will introduce the security problem that we are trying to solve in this work, namely microarchitecture or digital side-channel attacks. And I will also talk about why today's programming abstraction, which attempts to solve this problem, can fail on modern processor, as well as our proposed approach, data obliviously ISA or OISA extensions. Then I'll briefly go through the hardware implementation, security analysis, and the evaluation. Nowadays, microarchitectural side channels have been a huge privacy threat. The root cause of this attack is the resource sharing between user programs. It's difficult for programmers to defend against this type of attack because almost the entire hardware is made invisible to the programmer. For example, cache, in this case, is a fast storage for storing frequently used data. By observing that address 1 is loaded from the main memory to cache, the attacker who is co-locating with the victim on cache can learn the value of secret. Actually, modern processors are much more complicated than this. In addition to multiple layers of caches, we also have multiple layers of abstractions, for example, multi-core, multi-socket, and virtualization. And various of attacks have been proposed to attack all these hardware structures. So the rest of this talk is about solving microarchitectural side channels stemming from a software adversary who is co-locating with the victim and trying to monitoring the resource contention and program timing. So why microarchitectural side channel are big issues? So the most important problem is that there's no contract in the middle of hardware and software. Therefore, software does not know what can leak in the hardware, and hardware does not know what is secret in the software. Fortunately, programmers have already come up with a good programming abstraction to solve this problem, which is called data obliviously programming. It's worth to mention that different communities have different names for it. However, the basic idea is the same. By removing data-dependent behavior from the program can be executed inside hardware in a data-independent manner. Here we have an example. So this code has data-dependent behavior because the path taken by if depends on secret. We can then compile it into a data oblivious machine code in which we evaluate both paths and merge them with a ternary operator, cmove or cswap. We can even represent this data oblivious program with a data flow graph with static dependencies, as shown on the right-hand side. So the security of data oblivious programming is actually based on 3 assumptions. The first assumption is that within this data flow graph, each node actually is instructions processing private or public data. To achieve data obliviousness, we require that each instructions should be evaluated in a data-independent manner. And the edges in this graph is actually data transfers within and across hardware structures. So our assumption here is that the data transfer must be happened in a data-independent manner too. The overall structures of this graph actually represent what instructions are executed during the program execution and in which order are they executed. So the assumption here is that the instruction sequence should be fixed regardless of program data. So there are several reasons why data oblivious programming can fail on modern processor. The reasons are security, portability, and efficiency. Security is the first order problem since different hardware optimizations can undermine all these 3 assumptions. Despite our assumption that each instruction should be executed in a data-independent manner, actually different hardware optimizations can undermine all these security rules. For example, we have input-dependent arithmetic, microcode, or silent stores. The story is the same for data transfers since different data-centric optimization can actually cause data transfer to be revealing the relationship between data programs. So the violations are like database compression and microcode fusion, etc. Third, the instruction sequence can also be subverted by the hardware optimizations, as modern processors leverage optimization called speculation to improve performance. However, due to speculation, some instructions which should not be executed in a valid execution will be executed. So in this case, in this simple example, we can see that the speculation can cause some instruction in the original program execution to be replaced by some gadget that can reveal the secret to the attacker. The second reason is portability, since different hardware machines have different optimization enabled. So a code which runs safely on one machine may not remain secure on another one. So for example, a program which runs safely on processor A without branch prediction can suffer from attacks like Spectre if it's running on a processor B with branch prediction. Third, data oblivious programming is inherently inefficient, since we are basically traversing all the execution path in the original program. And the case can be even worse for memory operations, since we may need to touch the entire memory to hide the private address. So in short, the problem with data oblivious programming is the lack of a contract. For security, due to the lack of contract, the hardware does not have any obligation to follow all these three assumptions. And again, for portability, no constant contract exists across hardware implementation to specify the security rules. And for efficiency, since software does not know what can leak in the hardware, it's forced to use the simplest operations to implement complicated operations. And in this case, it will incur high performance cost. So to solve this problem in this paper, we augment data oblivious programming with an instruction set architecture, or ISA. So first of all, what is an ISA? An ISA is a contract between software and hardware. It provides the functional definition of all operations supported by the hardware, without any guarantees of how these operations actually implemented. So the programmers will only see a table of instructions and the instruction format like this, indicating which operations are supported and how to express them. So in data oblivious ISA, we are specify all the security properties that software require hardware to provide at the ISA level. So data oblivious ISA is the right solution because it can tackle all the three problems we mentioned before. It solved the security problem as we extend the base ISA. Therefore, it tells software what operation leak and what operation do not leak. And it also tells hardware what data is confidential or not. We also solve the portability problem, since ISA as well as the security specification is fixed across hardware implementation. Therefore, all hardware correctly following Oblivious ISA provide the same security protection. In terms of efficiency, by adding the security semantics at ISA level, the hardware is allowed to optimize the expensive data oblivious operations, such as load with private data. So data oblivious ISA extension consists of two base mechanisms. First, it dynamically differentiates between public and confidential data via a new type of dynamic information flow tracking. So it provides hardware the knowledge of what data is confidential. Second, it statically indicates what operations are safe to leak the confidential data. We rely on a new notion of safe instruction operand. So this mechanism provides software the knowledge of what operations leak and do not leak. Therefore, we add the security specification to the contract. So our new type of DIFT is work as the following. So at programming time, programmers declare data as either public or confidential. So the confidential data is tracked in hardware using DIFT. We'll reuse the security policy of the traditional DIFT, as the output will be marked confidential if any input is confidential, as shown in this figure. However, the difference is that traditional DIFT only tracks the retail data, but our DIFT tracks data at all stages in the instruction's lifetime. So at a high level, public data needs no protection. Therefore, we can activate all our hardware optimizations to improve performance. However, confidential data must be protected in a proper way. So the other component is new instruction with Safe Operand. we extend the ISA so that each instruction input operand is defined as either safe or unsafe. A safe operand means that all side channels stemming from that operand is blocked if necessary. And an unsafe operand means that there's no protection, so we enable all the hardware optimizations. So example here is a multiply with two unsafe operand. In this case, a optimization called zero skipping can cause side channel as input depends on timing, because the computation can be skipped if we see an input is 0, because the output is obviously 0 too. But in this graph, if we use multiply operations with safe operand, we cannot do the zero skipping anymore, because the input, which is 0, in this case register 2, is marked as confidential. However, we can do the zero skipping if register 1 is instead marked as 0, because register 1 in this case is identified as public, and it's fine to leak a public value via hardware optimization. So in total, there are 4 transitions can happen at runtime, and our mechanism to deal with all these 4 transitions is shown here. So we provide no protection when seeing public data provided as a safe or unsafe operand. We will disable all the hardware optimization when seeing a computational data provided as a safe operand. We will stop the speculation if seeing a computational data provided as an unsafe operand. But if it's not caused by hardware speculation, then we must stop the execution. The complete scheme combining both safe operands and DIFT works as the following. First, RSA designers decide instruction with safe and unsafe operands. Second, hardware designers will augment processors with logic to disable and enable optimizations. So at programming time, programmers will annotate some programming input and static data as confidential, so the rest are public. And the data of the RSA will enforce that this program running on this processor is independent of confidential data by enforcing these 4 transition rules and attain propagation during runtime. So in addition to our basic security protection mechanism, I would like to highlight 3 key benefits of data of this ISA. First, in terms of portability, it's a simple portable guarantee for programmers across implementation. In terms of efficiency, it actually opens up a huge design space for hardware designers to explore the opportunities for safe optimizations. And the third, it can actually defend against both non-speculative and speculative side channel attacks. So to the second point, we can actually achieve substantial speed up by implementing high performance instructions with safe operand. For example, we can address the performance bottleneck of sensitive loads by actually support fast load with safe address by either scan the entire object in O(n) time or using cryptographic techniques such as Oblivious RAM in O log n or log squared n time, or achieve O1 efficiency with hardware partitioning. And the hardware designers can even design more instructions to support more complicated operations, such as oblivious shuffle instruction, oblivious sort instruction, and etc. Another major benefit of DIFT is that we're able to defend against both non-speculative and speculative side channel attacks. So for non-speculative attacks, we can disable the hardware optimization when seeing a computational data is provided as a safe operand. But if we take hardware speculation into account, due to hardware misspeculation, some instructions which should not be covered in a valid execution can be executed. So those instructions may cause computational data falling to unsafe operand. Although the hardware misspeculation can be corrected afterwards, the side channel leakage has already happened due to this transition. So in this case, we must stop its speculation before the leakage happened. So in hardware implementation, we did the hardware prototyping on RISC-V Boom processor, which is a superscalar out-of-order core with different hardware speculation schemes. And we enumerate some potential side channel exploits of Boom in the paper, and we also proposed a OSA extension for RISC-V instruction set. We also implement some new instructions as shown in this box with Safe Operands and DIFT in Boom. And in the security analysis, we tried to formalize the security of data oblivious ISA extension. So as you know, when a processor is executing a program, it actually generates a trace of observable processor states. Example of this trace will be like the values of a subset of all the registers and memory cells in that processor at every cycle. So this trace actually represents the observation of the attacker throughout the program execution. And our goal is here to prove that this trace is actually independent of the computational data. So there are two challenges here. First is how to formalize the attacker's capability of observing processor states. And the second challenge is how to model the complicated modern processor with different hardware optimizations. And to address this point, we designed an abstract boom machine. So for more details about our answers to both two challenges, please read the paper. In evaluation, we proved that OSA can actually provide speed up for many database programming benchmarks. And in the case of constant AES and memory oblivious library, we also see significant performance improvement. So in conclusion, database ISA decouples security from functionality and implementation. So software receives consistent, portable security guarantee, and hardware is not constrained to specific implementation. And it's also a solution that can be applied to both speculative and non-speculative side channel attacks. So this is the end of my presentation. Thank you.
Hey, thanks for the talk. Alex Gampon from Qualcomm. So I think I missed. How do you trap when confidential data makes it to an unsafe operand? Do you have different types of memory now? You keep confidential data separate from non-confidential data?
So in processor pipeline, we track this by you adding like extra tag bit to the registers and all the pipeline registers in the pipeline.
No, but like in the Spectre example, right? The data that was meant to be confidential may not have been in the pipeline before at all, right? So you're exploiting some unsafe code that was meant to handle unsafe data,
yes,
to go and fetch some safe data.
So first, we must guarantee that all your computational data and all the data that has information flow from the computational data you specified is tagged as confidential in the pipeline. That's the first guarantee. And with that guarantee, when we have like branch misprediction or some like invalid instructions which want to like leak those computational data through like side channels, then it will actually happens what we call computational data to unsafe operand, this transition.
I guess I'm missing that first part, the precondition. How do you make sure that all the confidential data gets tagged in the pipeline?
First, the programmers will define what is your confidential data in the program at program level. And when you specify that, we will have like the tag bits embedded for every registers that indicating that this register is confidential.
But okay, anyway, well, we can take it offline.
Yeah, we can take it offline.
Hi, Gantan from Penn State. So I may have missed it, but I think you need a compiler to compile software to this architecture,
yes,
right?
Yes, definitely.
Right.
Yes.
So in the compiler, you kind of have to perform static tainting, which can possibly over approximate, what may be safe or maybe unsafe in your case.
Yes. So we need a program to actually correctly compile the code so that all the operations that operate on the computational data is marked as like safe instruction with safe operand. We need that. So the problem you asked, I think that's majorly depend on the compilers. But what hardware can do is that if the compiler makes any mistakes, then we promise that the computational data will not be leaked at hardware level.
Do you have a compiler already, or
no? We have.
Okay, thanks.
Hi, thank you for the nice talk. Regarding the dynamic information flow tracking system, do you propagate the taints in the indirect flows? For instance, when you have a control flow dependency or an address flow dependency, do you propagate the taints or not?
We propagate the taints, yeah. So propagate in like experience flow at register level.
Sorry?
So we propagate the taint in an explicit flow way at register level.
Okay, and where do you store all these taints and all this information?
So, as I said, in the pipeline, we have taint bits associated with each register.
How many bits?
Like 1 bit, you only need 1 bit for every register.
Okay, okay. Thank you very much.
Okay.